So I'll just make a little disclaimer before I do start the presentation, and that's all the observations and all the readings and everything in this presentation are my own readings and my own personal beliefs. I'm not saying these are the facts. I'm just saying from my observations I've come to these conclusions. Two things as well I want to say is, first, I'm no Steve Jobs, so presentation skills aren't at the top of my list. Yeah. And another thing, am I a scientist? No, I'm not. Yeah, I'm just a normal person.
You probably are the modern day scientist, aren't you, Dave?
Well, I suppose when you're making observations and you're recording it, I suppose everybody can be a scientist, can't they?
Yeah, so, but you're more real than the rest.
Yeah. So my presentation, Moon Race, the motions of the moon from a flat Earth perspective. Obviously, you've got your globularists who like to do their observations from their perspective, and I've got my own perspective for making observations for the moon. So I'll just tell you a little bit about myself. My name is David Marsh. I'm 46 years old now, just had my birthday.
Happy birthday.
Another year closer to death.
Oh, Dave, I'm older than you. Shh.
That's one way of putting it. Yeah. So I've been doing research in flat Earth probably about 2.5 years. I think it was around about November 2015 when I first stepped onto the flat Earth. And I've spent the majority of the time observing the moon because I've always been fascinated with the moon, and like I said before, if I can just concentrate on one aspect of flat Earth and maybe just find one little piece of that puzzle, I'll be happy, and hopefully I can wake up a few people on my journey.
Yes, Dave.
So
I'm one of them.
Yeah. So the history of flat Earth. Yeah. Some people think flat Earth's pretty new, but let me tell you, it goes back hundreds, if not thousands of years. Yeah. In fact, we've been questioning the shape of the Earth since the beginning of time, right back to the early Egyptians, if not before then. The only people who actually thought we lived on a globe was the Greeks. So it's not a psyop. And even in the 6th century, there was a guy called Cosmas. He'd written a book called The Christian Topography, which even in the 6th century, he was debating his fellow monks in regards to the shape of the Earth. They were still talking about the shape of the Earth then, and it's gone right through, even though it did get buried a little bit between the 6th century and the very, very early 1800s, but it for some reason there was an explosion again in the 1800s where you got Carpenter, Rowbotham, Williams, quite a few flat earthers. Lady Blunt was another one, Albert Smith. A lot of flat earthers seemed to come around about the early 1900s, but after World War One, boom, gone again. See, these wars, you know what I mean, they drain you as a nation, and well, you have to start rebuilding after that. And that war just came at the right time because I think flat Earth was trying to be forced into schools around about that time. And Alex Gleason was actually trying to get his information in the schools back in the day. So flat Earth is not a psyop.
There is absolutely no basis at all for thinking the world is flat. Nobody in human history, as far as I know, has thought the world was flat.
That was a message from Brian Cox, and he's saying nobody in history ever believed the world was flat.
Well, that's a lie.
I said, hey, it's nice try, Bri. Yeah, because every single ancient civilization in history believed the Earth was flat. From the Egyptians, the Norse, the Hindus, the Incas, the Navajo, the Hebrews. Every single civilization thought the Earth was flat, except the Greeks. And that's questionable as well. So, but even though the Greeks thought they lived on a ball, they thought they lived on a stationary ball at the center of the universe. So it was actually a geocentric model in itself. So, flat Earth proof. I just wanted to say, when I'm referring to flat Earth, I'm not referring to the Earth as some kind of a pizza floating in outer space. Yeah, I'm referring to there being no measurable curvature over large bodies of water. A good example of no measurable curvature over large bodies of water was the famous Joshua Nowicki shot taken from the Chicago skyline from Lake Michigan. I think it was about 46 miles the distance, and it should have been God knows how many feet below the horizon, but it shouldn't have been visible. That is a fact. But the interesting thing is on that one, when someone sent Joshua Nowicki's photograph into Fox News, they turned around and said the conditions are right on Lake Michigan for there to be a superior mirage. So they basically turned it into a superior mirage. But Rob Skiba did a little experiment where he actually filmed the Chicago skyline, and he basically powered his boat from basically one end to the other and kept the Chicago skyline in his viewfinder all the time. So clearly it's not a mirage, but you do get a lot of refraction on the lake at the times, depending on the atmospheric conditions, but it shouldn't be available to see. And what you will notice as well on the Chicago skyline, that the horizon line, if I could just get my mouse, is always at the eye level. Regardless how high you go, you always have the horizon at eye level. Even at 121,000 feet, you go to the Piggy Cam, which wasn't actually a flat Earth proof. It was just a video what was filmed from a high altitude balloon. You'll see that the horizon, or the horizontal eye zone, is always at eye level. Now that wouldn't happen on a globe. The horizon would roll away from you. But as you can see there, clearly the horizon is at eye level. And if you look at the size of some of them clouds down there, I mean, I bet them clouds are actually quite big clouds. There's quite a lot of ground it's covering there, because if you watch the camera carefully, it's not just swinging left and right, it's actually rotating left and right, you know what I mean? So you're actually seeing quite a lot of horizon skyline there. So that's quite interesting. Moving on to images of Earth. All I did here, I basically went onto Google, I typed in images of Earth, I clicked on images, and then I just took a screen snapshot. And that's what you get. There is no proper photographs of Earth, although they do claim the ones captured on Apollo were real, but they look a bit suspect to me. And as you can see, no two images of Earth look alike. Not one. Look, you say you start from the left-hand side here and go on. Every single Earth is different. I know some of these are actual composite images anyway, but these top ones here are supposed to all be real images of Earth, and you can see
They've drastically changed then.
Yeah, not one image looks like the other one. And funny enough, this is the guy who makes the blue marble, Mr. Blue Marble, aka Rob Simon. He's the data analysis for NASA, and he's been quoted in saying how he makes the actual globe is he takes a flat map and he basically wraps it around a ball. So that's how Mr. Blue Marble gets his nice, beautiful looking globe Earth. But
and
all
he still doesn't get it.
Yeah, it is Photoshop because it has to be. That's his own words.
Obviously paying him very nicely.
Yeah, so what are we told? Well, we're told that we live on a globe, and we're orbited by a single satellite, which we call the moon. The moon takes 27.3 days to complete its cycle, or one orbit of the Earth. But the moon phases take a little bit longer. They take 29.5 days. Now, the reasons why the phases and the cycle are different is because the cycle is based on what you call the sidereal, which is the stars, which basically says the stars to occupy the same spot the following night, it takes 23 hours, 56 minutes. But the phases are actually based on the sinusoidal day or the solar day, which we all know is 24 hours. Interestingly, there's quite a lot of different cycles on the moon. You've also got what you call a Saracen cycle, which takes something like 18 years. You've also got a cycle which goes from perigee to perigee. That's basically from this point here back to that same point. That cycle takes 27.5 days. So you've got various different cycles on the moon, and to get your head around all these different cycles, it's quite mind-boggling.
And look at the little globe going round and round.
Yeah, what I'm going to do, I'm just going to pause it here. Now, I'm sure many of you have seen a crescent moon at night time. In fact, I see one a few weeks back and took a photograph of it. What is interesting, when you see a crescent moon at night time, if you look at this little moon here, it's still in the path of the sun. So, like one day after a new moon, when you just see a little slithering of a crescent moon, it shouldn't be visible at night time because it's still in the actual light of the sun. So next time you do see a little crescent moon like that, tell yourself that should be impossible according to the heliocentric model, because the moon's still in the path of the sun.
But they don't want us to think. Well, I haven't done the thinking, you've done the thinking, and you've done the researching, but they don't want us as a people to think, do they? That's the point.
No, and that's why you've got the Gregorian calendar, because it's really confusing. It's got 28 days a year, 30 days there, 31 days there, leap year there. You know what I mean? It's all over the place. That's just the confusion. Turn your clocks back here, turn them forward there. It's all to keep you confused. Because if you had a basic 28 days and 13 months, it'd be too easy for you to work it out. So they make it very, very difficult for you to work it out.
Kepler's first law states simply that Mars travels in an elliptical orbit, with the Sun at one focus of the ellipse. Although he chose to list it first, Kepler only came to this conclusion after figuring out his second law, which says that if you draw a line from the Sun to Mars and wait a fixed amount of time, that line will sweep out a certain area as Mars moves along its orbit. What Kepler noticed was that this area is exactly the same no matter where in the orbit you are. This is often phrased as Kepler's equal area and equal time law, and this law works because Mars doesn't move at a constant velocity. It speeds up the closer it gets to the Sun. So if Mars is approaching perihelion, the point in the orbit nearest to the Sun, it's traveling faster than if it's at aphelion, the point that's farthest away. In the first case, the line connecting Mars to the Sun is very short, but because the planet is moving faster, it covers a lot of distance. In the second case, the line segment is much longer, but Mars also moves more slowly. Either way, the area swept out in a fixed amount of time is the same. Kepler and his contemporaries could see that Mars doesn't move at a constant rate, but they didn't know why. This inverse relationship that Kepler proposed between distance from the Sun and orbital velocity could explain the puzzling observations of Mars' movements, but only if the orbit is an ellipse. A circular orbit would mean no change in distance from the Sun with time, and thus the velocity would be constant as well. These two statements, that Mars travels in an elliptical orbit and that its speed varies so that the Mars-Sun line sweeps out equal areas in equal time, were generalized to include all planets in 1621, and they constitute Kepler's first and second laws of planetary motion.
Did you hear that okay, or was it too quiet?
Yeah, the very beginning bit we didn't, but we did hear most of that at the end. Yeah.
Well, don't worry too much about it, because I'm going to talk a little bit about Kepler's law now. Interestingly, when they showed that video, they actually debunked themselves by showing you that video, because the first thing what you'll notice on an elliptical orbit, you need two focus points or two foci for an ellipse to work. But you see, they've got the Sun in one focus of the ellipse, but there isn't a second focus point. Now, that should destroy the ellipse without that second focus point, because one single point will make a concentric circle. whereas they're telling us that the elliptical orbit's like slightly off-center shape. Yeah, but you need a second focus point for that. And interestingly, after Kepler's law of planetary motion, William Herschel actually set the sun into motion, because the sun was actually stationary up until that point, but he actually put the sun and all the rest of the solar system into motion, which then again absolutely destroyed the ellipse, because instead of getting elliptical orbits, then you got cycloidal orbits, or like spirals or springs. So he basically destroyed the actual ellipse. And not only that, Kepler's law of planetary motion was built up on the back of observations which were recorded by his predecessor, Tycho Brahe. Now, Tycho Brahe made his observations of Mars in the late 1500s. This was before the telescope was actually invented. So all Kepler's laws are built up on observations before the telescope was even invented. I know that they had some clever little gadgets back then, astrolabes and what have you, but compare Tycho Brahe's observations to my observations. I'm using the latest optics camera equipment, and I'm using GPS coordination to make my observations. So yeah, people mock me when they say, "Oh, you're debunking Kepler's law with a camera and a phone app," but I'm referring to, I'm backing up all my data with Mooncalc and time and date to make sure my readings are accurate. So they can mock, but we'll have the last laugh. Here's an interesting quote from one of our famous guys, Nikola Tesla. Today's scientists have substituted mathematics for experiments, and they wander off through equation after equation and eventually build a structure which has no relation to reality. Now that is so true, because there is no observation. There's only flat earthers making observations these days. All the rest are just equations. So that's an interesting quote. I'm sure you know who this guy is, Neil deGrasse Tyson. Neil claims that the Earth is a sphere, but it's not a perfect sphere. It's slightly oblate. It's an oblate spheroid. Not only is it oblate, but it's slightly chubbier below the equator. Basically, it's pear-shaped. Now, what I'm going to do, I'm going to just read you a quote out from Zetetic Astronomy from 1904, and it's on page 14. This is straight out of the book. It says, "Theory first of all makes the Earth to be a globe, then not a perfect globe, but an oblate spheroid, flattened at the poles, then more oblate until it was in danger of becoming so flattened that it would be like a cheese. And passing over minor variations of form, we are finally told that the Earth is pear-shaped, and the ellipsoid has been replaced by an apoid. What shape it may assume next, we cannot tell. It will depend upon the whim or fancy of some astute and speculating scientist." I think that's brilliant. Next, Neil will be telling us that they're shaped like a shiitake mushroom.
Sounds like they're trying to cover every angle.
Yep, it's amazing. Like I say, everything what spewed out of Neil deGrasse Tyson's mouth is just reciting from books. You know what I mean? It's a joke.
Yeah, agree with you on that one.
So my observations. What I did here, I used an app called Alptra, and I just set my compass at 0, well, nearly 0, and I just took a photograph with the app. It takes a little snapshot, and it gives you an azimuth reading and a declination angle. What you can see from that reading there is that the app I'm using, so it's a free app off Android. I think you can get an iOS version called Theodolite as well. I think you have to pay for that one though. But you can see it's pretty accurate. There you can see, look, I've placed it at north, and I've placed the app over it and took a little snapshot to show that the readings I am taking match up with the compass. So all my observations were made using the Nikon Coolpix B700. I always recorded at the same frame rate, which was 60 frames a second, the same zoom, which was about ×50, and from the same location, which was from my back garden in Ripley at the time. So I've always recorded my readings from the same spot. And not only that as well, I always try to catch the moon at my zenith, which was 180 degrees from my location at the time. Now I just want to give you a little bit of a comparison between flat Earth and globe Earth observations. On a flat Earth, one of the first things you'll learn about is perspective. And we learned that when an object, a celestial object, is closer to the observer, it will appear higher in the sky. And when a celestial object appears further away, closer to the horizon, that's how we judge it. That's how I judge it anyway, and I'm sure there's a lot of people out there who think the same. But interestingly, from a globe Earth perspective of the moon, when the moon's high on the Tropic of Cancer, it's not because it's closer to the Earth. It could actually be at apogee at that point in its cycle. It's because of that 5-degree inclination. That's what puts the moon high in the sky in their model. But from a flat Earth perspective, I judge it when the moon's high in the sky. I judge that moon being close to me, and when it's further away on the horizon, it's lower down. So when I was in the hotel at the convention, I come out to the corridor and I thought, wow, that's a long corridor. So I took a photograph of it, and what you'll see is these lights, yeah, they're all the same size. Let me just click back. These lights are all the same size, but it just looks like they're getting smaller and smaller and getting closer to the horizon, just like celestial objects do. The only difference with celestial objects like the moon is it doesn't get smaller as it goes further away. There is a reason for that, and it's called atmospheric lensing. That's why the moon, it actually gets bigger as it gets close to the horizon, because you're looking at the moon through more layers of atmosphere. It will appear bigger on the horizon than it does when it's up high in the sky, because you're looking at it through less layers of atmosphere, if that makes any sense. So my first observation, when the moon was on the Tropic of Cancer, and what you'll see here, the moon is in what I call the northern circuit, and it basically follows the actual stars. It does that all the time, and I took a snapshot on the 6th of March 2017. There you'll see the moon phase, which is a waxing gibbous moon. I also took a snapshot from NASA's Lunar Reconnaissance Orbital platform. Basically, this tells you the position of the moon from a globe Earth perspective. It tells you how close the moon is to the Earth. Obviously, when it's at 28 there, that's 28 Earths away. And when it's at its furthest point, that's 32. So the 28 would be perigee, and the 32 would be apogee. One thing what's quite difficult to get your head around, from a globe Earth perspective, when the moon would actually appear to speed up in the sky, it would be when it's at actual apogee. I know this is difficult to get your head around, but when it's at its slowest point in the cycle, that's when it would appear to speed up on a spinning globe. So just keep that in mind, because that does become quite important later on. But I did run this past my my old pal Chris Monk-Seeley, and he confirmed to me that from a globe perspective, the moon would actually appear to speed up at apogee and slow down at perigee. So that's just keep that in mind. So on the night of the 6th of March, I took a diopter reading, and as you can see, at that point, the moon was at 187 degrees, which is just roundabout south, where I always like to catch the moon at zenith, and it was high in the sky at 56.1 degrees. That's the declination angle. So it is quite high in the sky, as you can see there. I also compared my readings with Mooncalc. You know what I mean? It'd be a bit daft if I pointed my app at the moon. It said it was at 180 degrees, and I went onto Mooncalc, and it said it should have been at 270. There'd be questions being asked. So as you can see, their readings on the time of my observation was 183 and 55 degrees. If I just click back, you'll see mine are 187, 4 degrees out, yeah, and a little bit out on the declination angle. One thing you have to keep in mind, yeah, I'm using a phone app which uses GPS, and you have to calibrate it. So you basically have to swing your arms around like a madman in your garden and do somersaults and all sorts to try and calibrate the actual app. And even if you move like a millimeter, it can be the difference of like 4 or 5 degrees. It's so difficult to get it absolutely spot on, but it can be spot on, and I'll prove that later on.
360 things, don't you, to go round like that?
Yes, yeah, you have to tilt it, you have to swing your arms around, you have to do all sorts to calibrate it. But it is pretty accurate. Like I say, it's not too far out. As you can see, look, 55 and 183 and 56 and 187. So it's fairly in the same direction that I'm pointing, where it should be. That to me tells me that my readings are pretty accurate. So then, 1 week later, when the moon crosses the equator, as you can see, it travels in a fairly straight line when it's on the equator. Interestingly, the moon crosses the equator 26 times a year compared to the sun, which only crosses it twice. Not a lot of people know that. Well, they probably do now, like, but I didn't know that when I first started researching flat Earth. I thought the moon followed a similar path to the sun, but it clearly doesn't. So then again, on the 13th, a week later from my first observation, on the 13th of March 2017, the moon was nearly at full. So I took a little shot of the moon there. And also I took a snapshot from NASA's Lunar Reconnaissance moon phases. Interestingly, the moon's in the night sky there, and on a rare occasion, you can see a full moon in the daytime. That should be impossible in the heliocentric model. Just like an eclipse, when the when the actual moon rises in the daytime, already eclipsed. It's impossible. It should be impossible, but it happens. But they've always got an excuse for it. I can't remember what the name of it is, but it's got a name for it. It's got a really stupid long name. I'll look it up after and find out. So then again, I took another reading on dioptra, 182 degrees facing south again, and you'll notice the declination angle now has dropped down to 39 degrees because the moon's heading south, so it will appear lower on the horizon. A confirmation with Mooncalc. Moon azimuth on their website was 178 degrees, and the declination angle was 39. So again, 4 degrees out, which is acceptable in my mind. So I'll take that as being pretty accurate. So my third observation, when the moon, a week later, when the moon's on the Tropic of Capricorn, as you can see now, it's actually below that celestial equator, and it's in what I call the southern circuit. I'll just play that again so you can see it again. I'd just like to thank Jenna Fredo for the first time lapse from the Tropic of Cancer, and my good friend Jose Manuel Silva for this one he captured last year.
Smaller, isn't it, Dave?
Sorry?
Moon looks smaller.
Yes, it obviously with constantly changing atmospheric conditions, the moon will appear different sizes in different positions all the time. I'll pick up on that later on anyway.
Can I just say that Josh, Flat Earth Unity's joined us. He's from California. He might just be listening in, but he's joined the panel. Anyway, carry on, Dave.
Hello, Josh. Welcome, pal. So on my third observation, when the moon was on and around the Tropic of Capricorn. I captured the moon again. There you can see on the 21st of the 3rd, 2017. There you've got the exact same moon phase again. Notice the moon now, obviously it started here at perigee and it's heading towards apogee. I'll just go back and show you that just to give you an idea. There you see, it's heading towards apogee. So I'll just go back to that one. And there you can see it's nearly at apogee now. So when I made my first observation, it was at perigee, and now it's at apogee at its furthest point. Interestingly, this is where the moon should start speeding up in its cycle, but it shouldn't be like just a sharp increase in speed. It should be a varied increase in speed from one point to the next. So it should spend the first half of its cycle speeding up to apogee, and as it passes that point of apogee, it should spend its next point of its cycle slowing down. Even though that's the point where it actually speeds up on the globe, it will appear to slow down from a globe Earth perspective, like I mentioned before. There you see again, I took a reading. What you'll notice this time is I didn't quite catch the moon at south. There's a reason behind that. I've got a full-time job and I start work at 5:30 in the morning. As you'll see there, I left it as long as I could before I shot the moon. It was 5:16 and I then have to pedal 4 miles on my bike to start work at 5:30. So I was trying to rush the moon along to get in position, but I just had to take it as it was for that night, which I don't think it makes a lot of difference. So, but that's the reason why I didn't catch it at south. But you can see I took a moon count reading to match up there at 5:16. The reading is 159 azimuth and 15.1 declination angle. 158 azimuth on mine, 15.1. What I did then, I basically raced the moons against each other. So I also color coded them. So the moon, when it was on the equator, I've color coded yellow. The Tropic of Cancer, I've color coded red, and the Tropic of Capricorn, I've actually colored blue. I did actually get the idea from what's his name? The guy who was just messaged me. What's his name?
Stan.
Stan. Yeah, sorry, I forgot his name then. Yeah, I did get the idea. I did get the idea from Stan to color code them because it's a good idea because you can always refer back to it with the colors as well, which also makes it a good reference point. So thanks to Stan for that.
When you first did this, were you actually shocked at the result?
Well, yeah, because obviously I did my first observation. Yeah, and then on my second observation, the moon speeded up. So at the time, I was following the Circle AE map model. So I expected the moon to speed up on the Tropic of Capricorn. But what you'll see in a minute is quite interesting. So the fastest one was the moon on the equator. Then the Tropic of Cancer, and then the Tropic of Capricorn. In reality, the moon on the Tropic of Capricorn was just a tad faster than the moon on the Tropic of Cancer. Might sound a little bit confusing, but the reason behind that is, for some reason, even though I shot the moon from the same zoom, the moon appeared smaller that night in that position, and that's why the moon looks slightly smaller, but it was definitely shot from the same zoom, from the same location, which I've showed you from the diopter readings. It was all at the same position, but it did appear slightly smaller, which I did notice. But I went a step further in my next observations. What I'm going to do now, this is an example of how I collated all my data. I didn't just take somebody's numbers for it and use them. I actually went online and actually worked out the meridian passing times between the moon occupying one spot and occupying the spot on the following night. That's how I got my time frame or my marker to actually measure my observations against what the moon's actually doing. So for an example, on the first night on the 6th of March, what I did, I went on to the meridian passing on 6th and 7th of March, and I measured that time frame, and I used that to see if it was matching up with my observations. I have actually got a spreadsheet I'm going to get out in a minute, so I'm going to, here we go. Can you see that spreadsheet?
Yeah, we can.
That's good. So my first observation on March the 6th, you'll see the moon took 24 hours and 57 minutes to occupy the same spot on the following night. Then you notice a week later, when the moon speeded up on the equator, look at the meridian passing time there. It took 24 hours and 45 minutes to occupy the same spot. So what I'm shooting in reality is matching up with what's happening in reality. So I can say that my observations are pretty accurate, even though it's quite a crude way of recording the speed of the moon, letting it pass your screen on your camera. It definitely works, and I'll show you with my further observations later on in the presentation. And as you can see again, on March 21st, the moon actually slowed down. So that's what got me thinking about the circle model, that if you was on a circle model, wouldn't the moon speed up to cover the more ground? That was my thinking at the time, but I've moved completely away from models now. All I'm going to say is the Earth's flat because there's no measurable curvature over large bodies of water, not because it's a pizza or a Pac-Man or whatever you want it to be.
Yeah, we've kind of taken the same stance, really. We were a square flat Earth group, and now we've decided we don't mind the research like you, but we've kind of stayed away from what shape we are because everybody was arguing about. Well, anyway, carry on, Dave.
Yeah, that's a fair point, and that's the exact same reason why I came away from it, because I was sick to death of just seeing this post, that post, and it drove me crackers, and I just gave up in the end and thought, sod it, I'm just going to stick to the facts. There's no measurable curvature over large bodies of water, which FE Core proved a few weeks back when they measured 40 kilometers, which is 25 miles, over a lake in Holland, the Netherlands. So we'll just stick to the facts for the time being. So as you can see, them readings, there was all from my location, Ripley, UK meridian passing for March 2017. When I first posted my original moon race video, someone says, yeah, but when the moon's further away, it will appear to move slower because of parallax, you know. So when a celestial object is further away and it will appear smaller, it will take longer to actually cross your screen. So he says that's what would happen in reality. So what I did, I took readings from the equator. So I basically went on to time and date, exact same month, but I took the readings from the equator, and what you find is you get the exact same results. Yeah, even from their perspective, if you did the experiment from the equator, you'd get the same results. There you see on March 6th, 7th, the moon took 24 hours, 57 minutes to occupy the same spot. On the 12th, it speeded up, took 24 hours, 46 minutes. Remember, they're ahead of us, so it would have been actual there on their time, because there's quite a lot of time difference between the equator, especially in Pontianak, Indonesia. And then again on March 21st, 24 hours, 49 minutes. So that's from two locations, but I went even one step further then. I went to a place, well, I didn't go to a place, but I took readings from a place in Ushuaia, which is on the southern tip of Argentina, which is on the exact opposite southern latitude to the UK. And guess what? You get the exact same results again. So it doesn't matter where you are on the plane, the moon should always speed up from that perspective. So that's quite interesting in itself, because that surprised me, that I expected some slight variation in numbers, but they're exactly the same.
What, so you mean everybody in the UK will get the same kind of slow up, speed down, slow up, so it doesn't change Or, same in France, same everywhere else.
Everywhere you go, that moon will appear to speed up from their perspective. It doesn't matter where you go on the plane, New Zealand, Australia, it will always speed up. And time and date confirms that, which is very, very, very interesting.
Were you not expecting to see that, Dave?
Well, I was, but I was expecting to see a little bit of variation in the numbers, but they're nearly identical. And I bet if you took the actual times, you know, with the time difference from each location, I bet if you took that into consideration, I bet you'd get the exact same numbers. Because interestingly, I looked at the daylight hours from Ushuaia, and we get 17 hours daylight on our summer solstice on June the 21st, and Ushuaia on December 21st gets the exact same amount of daylight hours on their summer solstice, but on the opposite latitude. So that's quite interesting as well. And this is me hard at work. I just made a little time lapse of me actually collating the data. This is a 2.5 hour time lapse. I was going to put some Benny Hill music in it, some but I thought, no, I better not. But this is just to show you that, you know what I mean, I didn't just take somebody else's numbers for granted. I actually worked out the meridian passing data myself. As you can see there,
yourself.
you see how I sit up with my back, because my back's aching that much. I'm like trying to stretch my back at the same time. Look, that's why I keep sitting up like that. It's quite funny. Well, there I'm gone. And I'm back.
How long did it take you with the actual putting the numbers in and stuff?
It took me ages and ages, because I did it one at a time. I didn't only take readings from observations. I actually took readings for a full year between December 2015 and November 2016, when the moon was on the tropics and the equator. So I'll show you that in a minute, that graph, when we get to it, because that's interesting itself. So more observations. So we've seen now that when the moon leaves the Tropic of Cancer and heads towards the equator, it speeds up in its cycle. Not only my observations show that, but it's backed up by that meridian passing on time and date. And it clearly shows that when the moon leaves the Tropic of, leaves the equator and heads towards the Tropic of Capricorn, it slows down in its cycle. What I just want to show you now is it's not a fluke either. If you look at these readings, every single one in yellow there is when the moon heads from the Tropic of Cancer to the equator. And what you'll notice, it always speeds up at that point. Look, 24 hours, 42 minutes, 24 hours, 42 minutes, 24 hours, 43 minutes, 24 hours, 42 minutes, 24 hours, 43 minutes, 24 hours, 42. At that point, every single time. And what I did, I created a graph. And
oh my goodness, it looks a bit like a heartbeat.
Exactly. And I was talking to the guy at the convention who actually works in the hospital, and he says that is exactly the same.
Can I say something?
A heartbeat.
I know it's your presentation, and I don't want to interrupt you very much, but I've told you this before twice last year, when that moon came across on people are saying the moon equinoxes, or other people say that there's no such thing. But anyway, we'll call it that, because when it hits the Capricorn, Tropic of Capricorn, Cancer, sorry, I saw the moon come in at an angle, and then it went north for an hour, and then it went off. Just like that. Just like your graph. And it was dragging the stars. I told you this before. Yeah. Anyway, it does a sight like that. Just like that. Wow. Yeah. Anyway, carry on.
It's crazy, because like I say, every single one of them points is where it speeds up, but it looks like a heartbeat. And we all know that everything is electrical. If we die, touch wood, what do they use to bring us back to life? Electricity. Everything around us is electric. The sky's electric. Yeah, we generate magnetic fields, and so does the sky. And clearly, that the moon is like a pulse. If you put it into a graph, it looks just like a pulse. Like I said, that's a full year's readings on the tropics and the equator.
Wow.
So it just proves you that the moon, when it does speed up on the equator, it's not just a fluke. It happens regular, and that's over a full year. So more observations. So we've seen, I've just said this, but I'll say it again. We've seen the moon now that it speeds up when it leaves the Tropic of Cancer and heads towards the equator, but then it slows down. But what's the moon doing when it actually leaves the Tropic of Capricorn and heads back north to the Tropic of Cancer? Well, let's find out, because I've captured the moon coming back as well to complete the observations. So this time I waited till the moon was on and around the Tropic of Capricorn, as you can see there from my good friend Jose Silva. It's time lapse, and moon's below the celestial equator in what I call the southern circuit. Also, I just want to mention that everything I'm referring to in this presentation is celestial phenomena and not terrestrial. Yeah, there is a difference. Yeah, when I'm talking about poles, I'm not talking about geographical poles on a ball Earth. I'm talking about magnetic poles, like on a magnet. So I just wanted to make that pretty clear. I'm talking about celestial phenomena, which is measured in declination, and not terrestrial, which is measured in degrees. So on the 5th of the 8th, which is the 5th of August 2017, at exactly 11:40, on these observations, I went a step further. I included the times. Not only did I include the times, I've actually took measurements of the actual radius of the moon. Yeah, this is something I'm always improving my observations. Yeah, so this time I went one step further and actually measured the radius of the moon. And as you can see, on the night of the 5th of August, the moon, which was at its furthest point at apogee, measured 371.59 pixels. That's in actual pixels. You can see the little marker at the top there and the little marker at the bottom there, what I used for a measuring tool. As you can see, that's in moon phase, and you can see the moon is there at apogee. And remember, when the moon's coming back from apogee to perigee, it should speed up. Interestingly, we've already seen the moon speed up on the equator, haven't we? When it was heading towards apogee, which it shouldn't be doing anyway. Remember, it should speed up then, but it shouldn't speed up on the way back. That's it. Get me wires crossed. I'm sorted now. So just keep an eye on that moon, because that moon's going to be coming back towards perigee, and it should appear to retrograde or slow down in the night sky or the day sky, whenever it's visible. As you can see there, 5th of August 2017, same phase. I also took a diopter reading. What you'll see is the moon's low on the Tropic of Capricorn, and it's at 170.
Yes, I put quite a lot of readings in myself, as you well know, compass readings. And you can see, and I was putting them in, I could see at certain times of the month, the moon would be higher in the sky and lower in the sky.
Exactly.
Higher in the sky, lower in the sky.
It takes 2 weeks to go from tropic to tropic. So interestingly, that cycle from tropic to tropic takes 27.5 days, but the actual cycle takes 27.3 days. It's crazy. So the amount of different cycles there is. As you can see again, I took a moon calc reading. My readings are getting slightly more accurate because I'm taking more time and more care to try and make sure my readings match up with mainstream. So you can see there the moon declination angle, 17.3 degrees, and an azimuth reading, which is 178, which is only like 1 degree off south. And there you'll see my reading is 177 and 18 degrees. And then nearly a week later, when the moon was on and around the equator, remember it's coming from the south to the north now. So this is a time lapse actually capturing myself. Yeah, I used to love doing the moon time lapses. They turn out quite nice.
How much time is that when you do the time lapse on?
That's 2.5 hours. You get 10 seconds for 2.5 hours on a time lapse. Depending on your setting on your camera, because I think there's a different setting. You can change the frame rate and it changes the actual overall. I just leave the camera on 1080, 30 frames a second when I'm doing time lapse. But when I'm actually capturing the moon for my moon race videos, I always do it at 1080, 60 frames a second. And that's why I've had to upgrade my computer, because my last computer wouldn't run it at 60 frames a second. It used to be jerky as hell, but this one's nice and smooth now. So as you can see on my second observation, on the 11th of August, the actual radius of the moon is increasing. So that's actually doing what the heliocentric globe model's doing. It's following the right path there. So it's actually getting bigger as it gets closer, which is interesting. So 389 pixels compared to 371. As you can see, took another snapshot from NASA's Lunar Reconnaissance platform, and there you see the moon now is on or around the equator, exactly where it is from my perspective. So azimuth reading there, 179 degrees, bang on south, and a declination angle of 33 degrees, which is round about the celestial equator. Confirmation, see the nice straight line the moon travels when it's on the celestial equator. As you'll see there, look, their readings 179.6 and 32 degrees declination angle. Mine's 179 and 33. So I'm getting more accurate. In fact, if you look at that moon there, if I drop that down 1 degree, it'd be absolutely smack bang in the center. It's not easy pointing a camera phone at the moon and getting it smack bang in the middle.
Yeah.
Which you probably know yourself.
Yeah.
So my final observation, when the moon was on around the Tropic of Cancer, you'll see again, it's on the opposite side of that celestial equator in what I call the northern circuit. Now this is interesting, because when I measured the moon when it was on the Tropic of Cancer, it actually shrunk. If I go back to my last reading there, what you'll see, 389.5 pixels, 355 pixels. It shrunk. But according to the heliocentric model, it should have been getting bigger. And remember, that was at the exact same location and at the exact same frame rate as the previous shots. Interestingly, the moon was like monochrome that night as well. I could only, I've heard this on a couple of occasions, and a couple of my friends have posted this saying the moon, you can only shoot the moon in black and white. Sometimes you can only shoot the moon in black and white. Yeah, no matter what setting you mess about with on the camera, it always seems to come out monochrome. And this was one of them examples on that night when it appeared monochrome. You can see it there. It's got a slight grey color to it. The only editing on this picture I've done is by overlaying that measurement tool. That's the only editing I've done on that. That's basically a straight image from my camera onto the computer, and I just overlaid that to measure it. So, but interestingly, it shrunk. It went to 355 pixels. So, as you can see, the moon's getting closer to the globe Earth, so it should appear bigger. Let's just have a helio confirmation on that. So when
they have the same thing as like the sun. The sun gets smaller and closer, and then it's different when it's higher. It's warmer when it's higher. It's supposedly less. It's cooler when it's lower. Is the moon got the same kind of thing to it then?
Well, interestingly, you should say that. I've mentioned before. In fact, I come on your show and did a little presentation about it being impossible to have a full moon in the same hemisphere as the sun. And I think we went through a full year together, and I showed you from time and date that it's impossible to have a full moon in the same hemisphere as the sun. So whenever the full moon's out, yeah, it's always in the winter hemisphere. And that might be one of the reasons why the moon emits cool light on a full moon, because there have been quite a lot of experiments done in regards to measuring the moonlight. Yeah. But going back to the heliocentric model, at perigee, the moon is closer to the Earth and looks slightly larger. Now, I disagree, because when the moon is high at perigee and high on the Tropic of Cancer, it's like up in the sky and it looks tiny because you're looking at it through less layers of atmosphere. So I don't know how they can say that moon will look slightly bigger, because to me the moon looks slightly bigger when it's on the horizon, when you're looking at it through more layers of atmosphere. So I don't agree with that, because like I say, when I shot the moon on that night, it appeared smaller, and it wasn't, obviously according to their model it's supposed to be closer, but clearly it's small in the sky. And if anybody's seen the moon when it's high on the Tropic of Cancer, you'll see it's right up in the sky and it's tiny. So that was a bit of a interesting point. So again, took a diopter reading, 144 degrees at declination angle 48.1. You can see the moon's getting further and further north, and it's getting higher and higher in the sky. And just a quick reading there, you'll see 144 and a moon altitude or declination angle of 48.6. So again, my moon race for August. As you can see now, when the moon enters frame, it doesn't overexpose, because I'm learning new techniques with the camera, and I'm learning new tricks all the time, or new techniques. I learn as I go, basically. This moon race video is a lot better quality than the other one, a lot more stable, and the moon doesn't overexpose and look horrible as it comes into frame. I use what you call the AE lock feature on the camera. It's got it on the P900 as well. When you press record, you just have to press the little wheel to the right, and it locks the exposure and aperture and stops it overexposing. It's good for especially if you want to shoot like an occult, when you catch a star going behind the moon. It's brilliant for stuff like that, because you can just set it at the right exposure and lock it, and then you can obviously see both the star and the moon in the exact same focus, which would be impossible.
But you did it again, didn't you? Because you wanted to make absolutely sure of what you got the first time.
Yeah, as you can see, the moon on the equator took 5 minutes 20 seconds to cross my screen. On the Tropic of Capricorn, it took 5 minutes 36. But on the Tropic of Cancer, it seemed to take forever. It took 6 minutes 15 seconds to cross my screen. Look at the time difference there. That's huge. So the results. I need to just go back into my spreadsheet here. So what you will notice here, my first observations were made in August, but my third observation was actually made in September 12th. There is a reason for that, and the reason it was cloudy on the night I should have shot the moon, so I had to wait a full lunar month to get the moon back in the same position so I could shoot it again. It doesn't actually make much difference on the actual readings, because I'm still shooting the moon when it's high on the Tropic of Cancer. It's just that it was cloudy, and it was actually in daytime when I needed to catch it in August, which was quite disappointing, because when you've waited so long to get the moon in a position, and then you go out to shoot the moon and it's cloudy, it's like it's soul destroying.
So annoying.
And And that's one reason why I didn't do it with the sun, because if I'd have had to wait for the sun to get in that position, I'd have had to wait quite a long time to to get in that exact same position. So as you can see on August the 5th, my reading, the moon took 24 hours and 49 minutes for the meridian passing time on that night for the moon to occupy the same spot. Then when the moon was on the equator, the moon took 24 hours, 48 minutes. So it's speeding up when it's heading towards perigee. Remember, it speeded up when it was heading towards apogee. It can't speed up both directions. It's impossible. According to Kepler's law of planetary motion and his equal area and equal time law, the moon should spend the first half of its cycle speeding up with just a change in speed of around about 6%, and the same when it's going back the opposite direction. It should never speed up going to and from apogee. That completely destroys Kepler's law. It shouldn't do that. It's impossible. And you're probably thinking, yeah, but you could just put any of them readings on the screen yourself. You know what I mean? I've had to type them in there. But what I will show you in a sec gives you the confirmation first. So when the moon was on the Tropic of Capricorn, it took 5 minutes and 36 seconds to cross my screen, and the meridian passing on that night was 24 hours and 49 minutes. When the moon was on the equator, it took less time, so it was speeding up, and it took 5 minutes 20 seconds, and the meridian passing on that night was 24 hours 48 minutes. It's matching up exactly what I'm shooting in reality. And you know, the moon took a long time to cross my screen. It took 6 minutes 15 seconds. Well, look at the meridian passing time on that night, 24 hours and 57 minutes. It's matching up exactly what I'm shooting in reality. And just to confirm this, I took a little snapshot from time and date, and if you see on the 5th there, 23:39 till 12:28, yeah, you measure that time and you get 24 hours and 49 minutes, I think. Yeah. And then on the 11th, 3:40 to 4:28 is exactly 24 hours and 48 minutes. So what I'm shooting in reality is backed up by time and date. But interestingly, the moon shouldn't speed up when it's heading towards perigee. Although it speeds up in the globe model, from a globe Earth perspective, it should appear to slow down. So how can it speed up?
But quite often they show us some of the truth, and then they cover it over with lies, don't they?
Yeah, they never tell you the meridian passing. I've had to work that out myself. They tell you what time the moon crosses the meridian passing at zenith, and all I did was use their own information to measure the moon to see if it was matching my observations, which I clearly, you can see 100% there, look. It matches it perfect. When the moon took a long time, the meridian passing was longer. When the moon was shorter, the meridian passing time was slightly shorter. You know what I mean? It's absolutely perfect. And it was confirmed by the meridian passing from time and date for August 2017 when I made my observations. Sorry. So, magnetism versus gravity. This is an interesting quote taken from a book called Ether and Gravitation. It's by a guy called William Hooper. He's a globularist, but interestingly, he written his book, if either of these forces is to be done away with, it must be the mysterious, intangible, unphilosophic attraction of gravitation, which must be replaced by the philosophic and known attraction of electricity, which can be traced to a physical medium, the electromagnetic ether. He absolutely got it, absolutely smack bang on when he said that. Yeah, but then he backpedaled and says, no, it doesn't exist. It's gravity instead. It's mad. It just basically backpedaled at the end of the book and says, no, the ether doesn't exist. It's all gravity. But we know, everybody who's done their research into flat Earth knows that the only true force in nature is magnetism. And we're just going to see a little demonstration now of magnetism at work. There's no sound on this video, so I'll just let it play, and I'll just watch it with you. As you can see there, the magnetic field creates its own vortex motion, because electromagnetism is the only true measurable force in nature. It's the only force that can be measured. Trains in Japan, they don't run on anti-gravity. They run on magnets. So, my hypothesis. What do I think is going on? These are my own thoughts. Some people probably think I'm absolutely crazy in a minute, but this is
crazy. Appreciate all your research.
This is my hypothesis. Now, this image is always blown me away, because the actual bright spot is the moon overexposed, and what it did, it created a lens glare reflection and created an image of the moon. So that light there can create that image of the moon. Now imagine that on an epic scale, with the atmosphere acting like that lens and not the camera itself. Yeah, and that's when I come to the conclusion that the moon is basically a light in the sky, and it's some kind of projection. I'm not talking holographic images here. I'm talking like a natural projection. The light in the sky and the atmosphere acts as a giant lens, and it can create an image of the moon, which this image proves, because that doesn't look like the moon to me. Oh.
What does it look like? What do you reckon it? Oh, because it's so bright, you mean?
Yeah, look, how can that create that? It's an optical illusion. What we're seeing out in the sky is an optical illusion. The moon looks like it's probably about 10 miles away. It lights up the clouds locally around it. You know what I mean? If you look at the moon in the daytime, it's the actual image of the moon looks a bit fuzzy and not very clear, but at night time it always looks crisp and sharp, the image, you know what I mean? A bit like a rear projection screen telly. When you're watching in the daytime with the curtains open, they've got a rubbish picture, but you close the curtains and turn the light off and you've got a nice crisp picture. Same with the moon. I think David Weiss did some interesting experiments with the eclipse, where he showed a similar kind of projected light, and he basically cut that light out to make the eclipse. Might be worth having a little look at that video, what he made of last year, which was quite interesting, and I actually related to it to my research. And also that Steve Torrance and Mike Kavanagh come to a pretty similar conclusion in their electromagnetic Earth video, when they said that the orb of the sun is probably a type of projected image. I've come to the same conclusion, and I'm going to stick to my guns on that. So, the electromagnetic ether. We know that matter comes in three forms. You've got your solid, you've got your liquid, and you've also got gaseous as well. But there may be a fourth. Yeah, and that fourth element may be the electromagnetic ether, which is a luminiferous substance for the propagation of light. Basically, it carries all the heavenly bodies according to their frequencies, altitudes, and it carries them around the electromagnetic ether. And the ether is made up of two great vortices, or magnetic fields, and you've got one in the north. There's a time lapse with the camera pointing at Polaris. And you've got one in the south, which actually the stars rotate in the complete opposite direction. And that's from my good friend Paul Kofo, who took the shot facing south from New Zealand. If you put them side by side, there you'll see in the north, the stars rotate in a counterclockwise or anti-clockwise motion. And in the south, they rotate in a clockwise motion. Some people try and say that's perspective. I said it's two magnetic fields personally.
Like the magnets you were just showing us.
Yep. And just like a magnetic field, you see you'll have your vortex motion going one way, and on that field you'll have your, on the opposite pole you'll have your vortex field going the opposite direction. It always goes in the opposite direction.
Aha, see, that's what you see. You see that's not what everybody's rabbiting on about.
Well, like I say, some people will stick to a single pole vortex model. I'm past that. I believe that there's two poles, and remember, I'm talking celestial poles and not geographical poles like on a globe. I'm talking about celestial, not the terrestrial. I'm talking about the sky, not the land. And as you can see there, the moon, when it gets southern declination, it will basically cross the celestial equator, pick up on the ethereal currents in the opposing vortex, and be circling the opposite direction in the southern vortex. And then it will get northern declination, pick up on the northern currents, and be circling in the opposite direction in what I call the northern circuit. If you take a time lapse from around the equator, now if you move that land away, what you would see two vortex or vortices separated by the celestial equator. One goes one direction in the north, and one goes the other direction in the south. This is just to try and give you a visualization of what I believe the moon's doing. So when the moon is in the northern circuit, it will appear to circle, and as it picks up on the ethereal currents in the southern vortex, it will circle in the opposite direction. I know that might sound crazy, but if you go onto Mooncalc and you go to 70 degrees, what you'll find out is the moon will circumpolar from that observation. It'll be visible for 24 hours. So the moon will spend 2 weeks in the northern circuit in a counterclockwise direction. Then it'll spend the next 2 weeks circling the southern vortex in a clockwise motion. So it's basically going in a figure of 8. And I actually named it the lunar lemur. That's my own word I invented for that. We've heard of the analemma. Well, I actually made one up for the moon, and I call it the lunar lemur. And there you can see a snapshot of the moon over a 27, 28 day period. It clearly makes that figure of 8 pattern. And there's another snapshot over a period, similar kind of figure of 8 pattern. Interestingly, someone said to me, well, if the moon is on the southern circuit from your perspective, how the hell do you see it when you're in the north? But we have this thing called refraction. And what you'll see when a celestial object is perpendicular with the observer, you'll get less refraction. But as the moon, from my perspective, gets southern declination, or from the south gets northern declination, what it will appear to do, it will refract. And as that moon gets further and further away in the south, it will actually project further and further into the north. So it will be visible in the north, and going through quite a few layers of atmosphere, you will get something called refraction. And that's why the image of the moon will project itself into the north from the south. And here's an interesting daytime shot I took of the moon. I took a time lapse in the daytime, and you can see that the moon clearly emits its own light. It's not reflecting sunlight, it's actually emitting its own light. And I'll just click on that again so you can see it again. You can see the moon clearly emitting its own light, not reflecting sunlight. It does actually look like the sun, but trust me, that's the moon. If I took a time lapse with the sun without any filter on the camera, you wouldn't be able to see anything. That was the moon setting. So what is the moon? There's been a lot of questions about the moon over the years. Yeah, when you look at it,
I already said it's a chocolate chip cookie. Anyway, carry on.
Yeah, so I mean, when you look at the moon in the sky, it looks like a rock in the sky. It sometimes looks like a sphere. It sometimes looks like a disc. It looks like it emits. It looks like it reflects. Sometimes it looks solid. Sometimes it looks transparent or translucent. It's been there for a millennia, and we still don't understand what the moon actually does or what it is. We know the word month is derived from the word moon, but still, we still don't know what the moon is. And I think the moon could probably sit there for another 1,000 years and we might never, ever, ever know what the moon is. But I know one thing it's not, and it's not that. That's supposed to be the Discover Epic satellite, which is 1 million miles from the globe Earth, if you want to believe that bollocks. And as you can see, that's supposed to be the backside of the moon. I don't know what that green line is.
That one's a joke, though, isn't it?
Yeah, I think Rob Simon would probably say it is Photoshop because it has to be. But that is supposed to be a real image of the moon taken from the Discover Epic satellite 1 million miles out. And as I mentioned before, my goal or my agenda is just to find a little piece of that puzzle. If I can maybe contribute one piece of that puzzle towards finding out where we actually live, I'll be happy, and hopefully I can wake a few people up on the way. But that's my goal, just to find one little piece of that puzzle. And hopefully when I do get my own place, I will start doing some proper research. I can't really do it from me. It's a bit difficult. I'm having to set off an hour early from work. I get home an hour later. So time is a factor. But hopefully when I get settled down, I will be able to start doing some more research. I'm always looking at things and finding out things. So I'm not just sat here doing nothing. That's it. That's my presentation. I hope you enjoyed it.